So far, we've worked with systems with 0 solutions, 1 solution, and infinitely many solutions. And the system with infinitely many solutions often just takes some practice to get the consistency of writing the solution set. So that's what we're going to do here. We're going to take a look at 2 examples. Here we have this system, this 3x3 system. Remember, that means 3 equations, 3 rows. Each row is an equation, 3 variables. And we're going to begin to get this into a matrix form to solve it, but we see that the second 2 equations are not written in the proper standard format, so we're going to go ahead and rewrite those. The first equation is fine. The second equation will add 3y and 4z to the other side. We get 1x plus 3y plus 4z equals 0. And the third equation, we have 3x, but then we'll add 3y, we'll add 3z. And then we'll move the negative 60 to the other side. We'll add it, add 60 to both sides, so we get equals 60. By the way, which side you move things to doesn't make a difference. It's going to be the same equation. So for example, here if we had done negative x, we'd subtracted x, and we had negative x minus 3y minus 4z equals 0. That would have switched all of the coefficients here. And on first sight, that looks like a different equation. But if you divided both sides by negative 1, you'd get x plus 3y plus 4z equals 0. So it doesn't really matter which side you move things to. It just is a little bit more natural to move things to the left, move the variables to the left, keep the constants on the right. But that is not the only way to do that. Okay, so our matrix is going to look like this. 1, 1, 1, 20, 1, 3, 4, 0, 3, 3, 3, 60. Okay, and we're going to use Gaussian elimination to get this into reduced row echelon form. I've already gone ahead and typed in the matrix 1, 1, 20, 1, 3, 4, 0, 3, 3, 3, 60. And what we get is something involving some decimals. If you press this little button over here, it'll convert it to fractions to make it more exact, especially in situations where it's not. We get 1, 0, negative 1 half, 30. 1, 0, negative 1 half, 30. For our second row, we get 0, 1, 3 halves, negative 10. And for the third row, we get zeros. Now, do not judge the matrix by a row of zeros, because there are circumstances where there will still be just a unique solution. Read the equations off row by row until you get very comfortable with this process to where you might be able to see right away why there is 0, 1, or infinitely many solutions. So in this case, we know there are going to be infinitely many. So we have in the first row that x minus 1 half y, 1 half z, equals 30. Second equation says that y plus 3 halves z must equal negative 10. And in the third line, we have that 0 equals 0. Now that's, again, always a true statement, so that row just tells us that there's nothing to be concerned about. However, it doesn't tell me what x equals exactly. It does not tell me what y equals exactly, and it doesn't tell me what z equals exactly. So I know that there's going to be a free variable situation here, i.e. infinitely many solutions. So I'm going to identify my free variable. I can see that both of these equations depend upon z, that if you give me a value of z, I know without question what x and y will have to be. But I'm going to go ahead and analyze row by row. First row, the first non-zero value is in the first column. So that means x is not going to be a free variable. In the second row, we search for our first non-zero value, which happens in the second column. That means y is not going to be a free variable. Now, there's a third row, so we have to consider that third row, and we see that in the third row, there is no non-zero coefficient, and so that means that any variable that hasn't been considered yet is now free. So this is going to be a free variable. So we do this by saying, to write the solution set, again, we don't want to just produce a solution, we want to describe how to generate solutions. So we'll assign a value to our free variable. Again, z equals c just means we're assigning it some number. It doesn't matter what that number is. C is a real number. Okay, C is a real number. You'll often see it like this. C is an element of the real number. That just means that C can be any real number, positive, negative, fraction, decimal, zero, whatever we like. Well, in that case, that means that if Z is equal to C, that means that x minus 1/2 times C equals 30, or x has to equal 30 plus 1/2 of that value. In the second equation, what does y equal? Well, y is going to equal negative 10 minus 3/2 of whatever value we give z, which is this constant c. And then we can write our solution set x comma y comma z equals x, which is 30 plus 1/2 c, y, which is negative 10 minus 3/2 c, and z, which is the value that we fix initially. And you can test this out. Let's just say, for example, x is equal to 2. I pick 2 because then it cancels out some of the fractions, so that's nice. So we get x, y, z, in that case would be, we want z equal to 2. Then we get 30 plus 1/2 of 2 is 1, so 31. We get negative 10 minus 3/2 of 2, which is negative 10 minus 3, negative 13. And then the value of z is 2. So we can just check that these three add together to give us 20. 31 minus 13 is 18. 18 plus 2 is 20, so that one checks out. X has to equal negative 3y minus 4z, so negative 3 times negative 13 is 39. Negative 4 times 2 is negative 8. 39 minus 8 is 31, the value of x. So that checks out. And finally, 3x minus 60, so 3 times 31 minus 60. 3 times 31 is 60, no, 93. 93 minus 60 is 33. Negative 3 times y, negative 3 times negative 13 is positive 39. 39 minus 3 times 2 is 33. And so we get 33 equals 33 is a true statement. And so for that third equation, we have equality as well. So at least for z equals 2, we've done well. Another strategy would just be to plug in these actual values for x, y, and z into each of the equations and see that this is moreover a general solution. But picking an example is sometimes useful just to see that we found the solution correctly. All right, so moving on. Let's consider one with 5 variables. Oh, this looks tough, doesn't it? It looks like there's going to be a lot more to do here. But the beauty is it's the exact same process. So I do need to do a little bit of rearranging here. I see that the first equation is good. x1 plus x2 plus x3 plus x4 plus 3x5 equals 4. So let's just actually go ahead and try to write this by looking at it and see if we can do it. So we have 1, 1, 2, 1, 3, 4. 1, 1, 2, 1, 3, and then our constant 4. In the second equation, notice that we don't have x1 and x2 in the first row. We have 0x1 plus 0x2 plus 1x3 plus 2x4 plus 1x5 equals 1. In the third equation, I have 1x1, have negative 1x2, I have 0x3, I have 1x4, and then I'd have to add this x5 to the other side, so this would give me 1x5, and once I've added this over here, I get a constant of 0. Now one thing you might want to do is just label these columns so you make sure you're plugging in the correct coefficients. And of course these are the leftover residual constants on the right. And finally, in this last one, we're going to add the x4 over. So we'll have x2 plus x4 equals 6. So x2 and x4 will both have coefficients of 1. Have a 6 over here. And then we don't have an x1, we don't have an x3, we don't have an x5. We have 0 of them. Now we can produce the reduced row echelon form, that is, perform the Gaussian elimination and see what we come up with. Okay, so we do that. We have 1, 1, 2, 1, 3, 4, 1, 1, 2, 1, 3, 4, 0, 0, 1, 2, 1, 1, 0, 0, 1, 2, 1, 1, 1, negative 1, 0, 1, 1, 0, and 0, 1, 0, 1, 0, 6, 0, 1, 0, 1, 0, 6. Okay, good deal. So here is the result of the reduced row echelon form of that matrix. It's a non-terminating decimal, so not pretty, and it might make sense to convert it to fraction form. Easier to work with that way. So we have the first row is 1, then 3 zeros, 1 and 8/3. Then for the second line we have 0, 1, followed by 3 zeros and 13/3. And then for the third equation we have 0, 0, 1, 0, 1, negative 7/3. Oh, I put that in the wrong place. 0, 0, 1. That should be a 1 right there. And then finally, in the fourth row, we have 0, 0, 1, 0, 5/3. 0, 1, 0, 0, 5/3. I'm all backwards here. Let me try this again. Okay. 0, 0, 0, 1, 0. 5/3. All right, there we have it. So again, coefficients x1, x2, x3, x4, x5, constants. We're going to read off each of the equations line by line. So we see that there's no row full of zeros, first of all. But as we read into the first row, we see that x1 plus x5 equals 8/3. This is why it's so important to write these out. Second row, x2 is equal to 13/3. So we get a unique value for x2. It has to be 13/3. In the third row, we have that x3 plus x5 equals negative 7/3. And in the fourth row, we have that x4 is equal to 5/3. Okay, so if we look at this system, first of all, we see that we're all set with x2 and we're all set with x4. The other two equations don't involve x2 or x4 at all. Notice that x1 and x3, those two lines, they both depend on the value of x5, whose value is unspecified. Well, that's going to tell us right away that x5 is a free variable. But if we did this systematically, and we didn't want to overthink it, we look at the first row, find our first non-zero pivot, that's in the first column. So x1 is not going to be a free variable, and we see that it's not, it depends on x5. In the second row, our first non-zero pivot is in the second column, so x2 is not going to be a free variable. In the third row, we see that the first non-zero pivot is in the x3 column, so it's not going to be a free variable. And in the fourth row, we see that that occurs in the fourth column, so x4 is not a free variable. But since we've run out of rows and x5 has not been the first non-zero coefficient in any of the rows, x5 is the one and only free variable. And we've confirmed our instincts here. So if we assign x5 to equal some constant, where c is just an element of the real numbers, it's just going to be some real number, then our solution set will take on the following shape. Now, I'm not going to write this as an ordered quintuple, as we would say. I'm just going to write this out in a vector form. So I'll list out. Now, you can write it as just these 5 values separated by commas, but it's a little bit easier to read visually if you write it in this vector form. So x1, what does x1 equal? Well, x1 is 8/3 minus the value of x5. x5 takes on the value of c. 8/3 minus x5 will be 8/3 minus c. x2 has to be 13/3. No ifs, ands, or buts about it. x3 is going to equal -7/3 minus the value of x5, which is c. x4 equals 5/3. And x5 is going to equal the value that we choose to assign to it, which is c. So you can see that in rows 2 and 4 of this vector, those values have to be what we've specified them as. And the way we obtain that is just by carefully reading our reduced row echelon form matrix so that we could identify any free variables. And taking that time to cautiously do this produces this nice distinct result. Okay, very, very general form. There's our solution set. Again, infinitely many solutions. You're going to have that anytime you have a free variable. And assuming that we don't end up with a row that leads to a false conclusion of 0 equals 1. We can, at this point, choose a value of c. Although I won't do it here, you could pick c equals 0, for example, if you want an easy check. And then you'd have 8/3, 13/3, -7/3, 5/3, and 0 for your values of x1 through x5. And you can come back up here and plug them in and see that they make all 4 equations true. So this is a 5-dimensional problem and considerably small. We can think about this as maybe a company has 5 different products and it wants to know how much it's going to charge for each of them based on their desired profit and constraints upon those variables. And in this case, there would be infinitely many possibilities. Now, in practical circumstances, we would obviously want to limit ourselves to positive values, so we would need to think about what values of c might work. And that's something we'll visit when we start to contextualize this a little bit more. Now that we have all 3 of the different system types accessible and we know how to interpret them, we're ready to take a look at some contextual results.